Hi everyone. So, wanted to talk about quantum mechanics again, kind of reboot the subject a little bit, go through a progression that's a little bit more historical in nature, go back to the roots of quantum mechanics in the study of the atom and how that works. In general, there are three main categories of evidence for developing the theory of quantum mechanics. There are scattering experiments, there are decay experiments, and there are bound state experiments. So the scattering experiments are really what drive quantum field theory, some of the stuff we talked about in the last lecture series, video series. Decay states also are useful in that. The bound state, though, is really what we're going to be talking about here. We've got an electron bound to a nucleus. And how does that work? So, when Rutherford first discovered the nucleus via scattering experiments, the basic idea was that, it's a lot like the solar system. In the center, you've got a nucleus, which is represented by the sun, and around it are spinning electrons. The problem with this theory, which was immediately evident, is that if the electrons are moving in circles, then they must be experiencing some centripetal acceleration. But from electromagnetic theory, we know that when charges accelerate, they radiate. And so what that means is that the electrons in the atom must be constantly radiating electromagnetic energy. And if they're radiating that energy, they're losing the energy, which means that eventually the electron will spiral into the nucleus. Now, if you do the math, figure out how long that's going to take, it's on the order of picoseconds. In other words, the planetary model of the atom is extremely unstable. In fact, it just cannot be. It cannot work. So that's about 1911. A couple years go by, people are noodling over what could this possibly be? I mean, how does this work? Other sets of experiments were brought into play. One of the most important is this idea of spectroscopy. And in this example, you take a material here, maybe this is neon or mercury or something, and you run it through a fluorescent tube. Examine the spectrum of light that's radiated, and you find that it comes in very distinct spikes of frequency. Now this is a little odd. You would expect something to be more spread out, like a black body spectrum. And the fact that we've got these spikes is telling us something very important. It's telling us that the energy that's radiated from the atom only radiates at certain frequencies. So, hydrogen is the simplest possible atom. You've got one proton, one electron. And so a lot of emphasis initially was on investigating the spectrum of the hydrogen gas. And this equation was discovered kind of empirically in the 1880s. And basically what it represents is you've got two integers here, okay, and 1 and 2. It could be 1, 4, 6, and 3, whatever, right? You've got these integers, and if you calculate all the different combinations and calculate the wavelength associated with that, that predicts the pattern for the hydrogen atom. Now, where this formula comes from, no one knows, but at least it gives us a mathematical handle to start understanding some of these things. So, a couple of years after Rutherford, Niels Bohr comes along and says, I don't really understand what's going on, but let's make an assumption. Let's make an assumption the planetary model is correct. And let's also assume that for some unknown reason, the angular momentum is quantized. In other words, the angular momentum only comes in certain particular units. packets. And let's say it's related to Planck's constant, which he made a similar assumption regarding light, that light comes in discrete packets of energy. Bohr said, let's assume the angular momentum comes in discrete packets of angular momentum. And basically, it's some integer multiplied by h bar. H bar is Planck's constant divided by 2 pi. And this is the definition of angular momentum, mvr, for one particle orbiting. And if you use this, combine it with some classical arguments to derive energy and the distance associated with those angular momentum, and you have to roll in Coulomb's law. So basically, you take Planck's new assumption about angular momentum, combine it with Coulomb's law, derive the energy and radii associated with those orbits. And so this is the Bohr model of the atom. And this formula for energy exactly explains the Rydberg formula up here. And this is the picture you should have in your mind. You've got energy levels. This is an energy diagram. The lowest energy level here is kind of the central orbit. It's the n equal 1 value. At a higher orbit, an energized orbit, the radius increases because you've got more energy available. The potential energy increases. And so you've got an electron up here. When the electron radiates, it doesn't just fall. It goes from here to here. Bam! And all that radiation is emitted in one single packet. And that's the single photon packet that Planck developed. And so this is fundamentally the Bohr model of the atom based on this fundamental assumption. Where does it come from? Not sure, but if you make that assumption, then the rest of the theory follows. And so that really focuses us down to the question, where does this come from? And it also gives us a neat explanation for the spectra associated with the hydrogen atom or atoms similar to hydrogen. And it's important, 13.6 electron volts is the ground state energy. And so that's the amount of energy required to ionize, remove the electron, because the electron's got to move from this state to this state to this state to this state to this state until it's completely removed. And there you go.